Tonight, we're going to explore one of the most remarkable journeys in human history. Two spacecraft, launched in 1977, designed for a 5-year mission to study Jupiter and Saturn. They're still operational, nearly 50 years later, billions of miles beyond their original destination. And when they reached the edge of the solar system, they discovered something shocking. The boundary was 2.4 billion miles farther than every scientist predicted. The shape was completely wrong. The magnetic field behaved in ways no one expected. And the space beyond had properties that contradicted every model. 7 major discoveries that proved we didn't understand our own cosmic neighborhood. By the end of tonight, you're going to understand how 2 spacecraft built with 1970s technology rewrote our understanding of where the solar system ends and interstellar space begins. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The year is 1977. NASA launches 2 identical spacecraft on what everyone expects to be a 5-year mission. Voyager 2 lifts off on August 20th from Cape Canaveral. Voyager 1 follows on September 5th, taking a faster trajectory that will allow it to reach Jupiter and Saturn first. The names reflect their arrival order, not their launch sequence. Each spacecraft weighs 1,820 pounds. They stand 12 feet tall, and they carry a suite of instruments designed to study Jupiter and Saturn, the 2 largest planets in our solar system. The mission is called the Grand Tour, taking advantage of a rare planetary alignment that occurs once every 176 years. This cosmic arrangement allows the spacecraft to use gravity assists, slingshotting from one planet to the next, visit all 4 outer giants, Jupiter, Saturn, Uranus, and Neptune, in a single journey. Without this alignment, visiting all 4 planets would require separate missions and far more fuel than any rocket could carry. The planets have arranged themselves perfectly. NASA seizes the opportunity. The original plan is simple. 5 years. Study Jupiter and Saturn. Then drift into the outer solar system as the power fades and instruments go silent. No one expects these spacecraft to last beyond their warranty. No one predicts they will still be operational in 2026, nearly 50 years later. And absolutely no one anticipates that their greatest discoveries will come not from the planets, but from what lies beyond them, from a boundary that scientists thought they understood. But here's what scientists in 1977 believed about the edge of the solar system. They knew the sun constantly emits a stream of charged particles called the solar wind. This wind flows outward in all directions at speeds around 250 to 500 miles per second. It's a plasma, a soup of protons and electrons, so hot that atoms are ripped apart. The solar wind was discovered in the late 1950s and early 1960s. Eugene Parker, a physicist at the University of Chicago, predicted its existence based on theoretical calculations. He showed that the sun's corona, the outermost layer of the solar atmosphere, is so hot that it can't be gravitationally bound. The gas must flow outward continuously. Parker's prediction was controversial at first. Some scientists thought the solar wind must be transient, occurring only during solar storms. But spacecraft measurements in the early 1960s confirmed that the solar wind flows continuously, every day, every year, regardless of solar activity level. The Sun is constantly losing mass through this wind, about 1 million tons per second. That sounds like a lot, but the Sun is so massive that it would take trillions of years to lose a significant fraction of its mass this way. Eventually, this solar wind has to hit something. It can't expand forever. The galaxy isn't empty. Between the stars, there's gas. Extremely thin, but it's there. About 0.1 atoms per cubic centimeter. For comparison, Earth's atmosphere at sea level has about 10 to the 19th atoms per cubic centimeter. So, interstellar space is 10 to the 19th times less dense than air. It's a better vacuum than we can create in our best laboratories. But it's not nothing. Over cosmic distances, even this tenuous gas has mass, pressure, and momentum. The interstellar medium is also moving. Not because it has its own bulk flow, but because the Sun is moving through it. Our entire solar system orbits the galactic center at about 137 miles per second. That's about 490,000 miles per hour. From the Sun's reference frame, the interstellar medium is a headwind blowing past at that speed. Where the solar wind meets the interstellar medium, a boundary forms. Scientists call it the Heliopause, the place where the Sun's influence ends and true interstellar space begins, the place where the outward pressure of the solar wind equals the inward pressure of the interstellar medium. Beyond the Heliopause is space that's no longer dominated by the Sun. Space, where the galactic magnetic field dominates, where galactic cosmic rays flow freely, where the properties are determined by the galaxy rather than by our star. By the 1980s and 90s, scientists had built sophisticated computer models of this boundary. They ran three-dimensional magnetohydrodynamic simulations. These simulations included magnetic fields, plasma dynamics, and the effects of the Sun's motion through the interstellar medium. They predicted the heliopause would be roughly spherical, maybe slightly elongated, like a comet's tail. Maybe somewhat elongated in the direction opposite the Sun's motion, forming a tail, but basically symmetric. A bubble surrounding the Sun at a fairly consistent distance in all directions. They calculated it should be at about 90 to 100 astronomical units from the Sun. 1 AU is the distance from Earth to the Sun, roughly 93 million miles. So, 90 to 100 AU meant about 8.4 to 9.3 billion miles. This seemed reasonable, based on the data available. Models assumed the interstellar medium was fairly uniform in density and pressure. They assumed the Sun wasn't moving too fast through it. They assumed the solar wind output was fairly constant. All reasonable assumptions based on limited data available in the 1980s and 90s. They knew the solar wind's strength from measurements near Earth. They estimated the interstellar medium's pressure from astronomical observations. They ran the equations, 90 to 100 AU. That's where Voyager should cross. Before reaching the heliopause, the solar wind would encounter a shock wave called the termination shock. This happens because the solar wind is supersonic. It's moving faster than the speed at which pressure waves can travel through the plasma. The speed of sound in a gas depends on temperature and composition. In the solar wind plasma, the sound speed is typically around 30 to 60 miles per second. The solar wind is flowing at 250 to 500 miles per second, so it's moving at 5 to 10 times the sound speed. It's supersonic, or more precisely, supermagnetosonic, because magnetic fields affect wave propagation in plasma. When supersonic flow encounters an obstacle, a shock wave forms ahead of the obstacle. This is true in air, which is why supersonic aircraft create sonic booms. It's also true in plasma. At the termination shock, the solar wind would suddenly slow down from supersonic to subsonic. From about 250 to 500 miles per second, down to maybe 50 to 100 miles per second. The plasma would heat up and compress. The density would increase by a factor of 3 or 4. The temperature would jump by an even larger factor. Energetic particles would be accelerated by the shock, boosted to high energies by the electromagnetic fields associated with the shock structure. Models predicted the termination shock would be somewhere around 75 to 90 AU, somewhat closer than the heliopause itself. The exact distance would depend on solar activity. During solar maximum, when the sun is producing more solar wind, the increased pressure would push the termination shock farther out. During solar minimum, less solar wind, and the shock would move inward. Between the termination shock and the heliopause would be a region called the heliosheath. Solar wind plasma that's been slowed and heated, flowing generally outward, but also sideways, trying to move around the obstacle of the interstellar medium. The flow in the heliosheath wouldn't be smooth. It would be turbulent, filled with magnetic field irregularities and plasma instabilities. But it would still be dominated by solar material, particles that originated from the sun. The heliosheath was expected to be perhaps 10 to 20 AU thick, a transition zone between the shocked solar wind and true interstellar space. Beyond the heliopause, galactic cosmic rays would dominate. High-energy particles from supernova explosions and other violent events across the galaxy. These particles are mostly blocked from the inner solar system by the sun's magnetic field and the solar wind. They can penetrate into the heliosphere, but their intensity is reduced. The heliosphere acts as a shield, deflecting or slowing many cosmic rays before they reach the inner planets. But beyond the heliopause, their intensity would increase significantly. Models suggested cosmic ray intensity might double or triple compared to levels at Earth's orbit. The transition across the heliopause should be fairly sharp. Models suggested it might take a few weeks to a few months at most to cross from the heliosheath into interstellar space. The spacecraft should see solar wind plasma disappear suddenly, or at least drop to very low levels. Galactic cosmic rays should suddenly increase. The magnetic field direction should change as the spacecraft encountered the galactic magnetic field instead of the sun's field. The galactic magnetic field was expected to be oriented differently from the sun's field. The sun's field in the heliosphere runs generally radially outward from the sun, though twisted and tangled by the sun's rotation. The galactic field should be oriented based on the large-scale structure of the Milky Way. Models suggested it should make a significant angle relative to the radial direction from the sun. So at the heliopause crossing, instruments should detect all of these changes. Plasma disappearing, cosmic rays increasing, magnetic field rotating to a new direction, all happening over a period of weeks to months. Scientists were confident in the basic picture. The equations of magnetohydrodynamics were well established. The physics of shocks and plasma dynamics had been studied for decades. The models had been refined and improved over years of work. They might be wrong about the exact distances, but the overall structure should match the models. A termination shock around 75 to 90 AU, a heliosheath 10 to 20 AU thick, a heliopause around 90 to 100 AU, a clear, relatively sharp boundary separating solar and interstellar space. But they were wrong, not slightly wrong, dramatically wrong. And that was just the first surprise. Understanding what makes these discoveries so remarkable requires understanding the technology that made them possible. Because what Voyager accomplished, it accomplished with equipment designed and built in the early 1970s, before personal computers, before the internet, before cell phones. The computers aboard each Voyager are absurdly primitive by modern standards. Each spacecraft has 3 computer systems working together. The computer command system handles instructions from Earth. The flight data system processes science data. The attitude and articulation control system manages orientation and pointing. Together, these 3 systems have about 68 kilobytes of memory. Your smartphone has millions of times more memory than both Voyagers combined. Yet, engineers can still upload software patches to these machines. In 2002, NASA uploaded new code to Voyager 1 to work around a failing memory module. In 2013, they switched Voyager 2 to backup thrusters that hadn't been used in 37 years. The thrusters fired perfectly. Imagine debugging software written 50 years ago, running on hardware you can't touch, where every command takes over 22 hours to reach its destination. Power comes from radioisotope thermoelectric generators, RTGs. 3 per spacecraft. They contain plutonium-238, which decays naturally and produces heat. Thermocouples convert that heat into electricity. At launch, each spacecraft generated about 470 watts. But plutonium decays over time. The power output drops steadily, about 4 watts per year. By 2026, Voyager 1 has only about 249 watts remaining. This declining power is the ultimate constraint. Every instrument, every heater, every transmitter draws from this dwindling budget. As power drops, engineers must decide what to shut down. The cameras went dark in 1990. Various instruments have been turned off over the years. By the late 2020s, there won't be enough power to run anything. The spacecraft will fall silent. Communication happens through the Deep Space Network. 3 massive radio antenna complexes in California, Spain, and Australia. Spaced around Earth, so at least one always has a view of the spacecraft. Each antenna is 230 feet in diameter. The signal from Voyager 1 takes over 22 hours to reach Earth. The signal from Voyager 2 takes about 18 hours. When engineers send a command, they wait those hours for it to arrive, then wait again for confirmation. A simple exchange takes over 44 hours for Voyager 1. The transmitter power from each spacecraft is about 23 watts, less than a typical LED light bulb. By the time that signal reaches Earth across billions of miles, it's incredibly faint, 1/quintillionth of a watt. The faintest signal humans routinely detect and decode. This is the technology that discovered what lies at the edge of the solar system. Computers with less memory than a microwave oven. Transmitters weaker than a refrigerator light bulb. Instruments designed with slide rules. Keep this in mind as we explore what they found. Because what comes next shocked every scientist who studied the data. Voyager 1 reaches the termination shock on December 16, 2004. The spacecraft is at 94 AU from the Sun, 8.7 billion miles. Scientists had predicted the termination shock would be at 75 to 90 AU. Voyager is already beyond that range. The termination shock is where the solar wind suddenly slows from supersonic to subsonic speed. It's a real physical boundary where the plasma compresses and heats up, and Voyager just found it farther out than expected. But here's where it gets strange. The crossing isn't clean. Voyager detects the shock on August 1st, 2002 at 85 AU. Then, the shock moves. Over the following months, the boundary shifts outward. Voyager finds itself back in supersonic solar wind. The signatures of the shock disappear. In 2003, Voyager detects it again. The shock washes over the spacecraft as it moves outward, then retreats. Finally, on December 16, 2004, Voyager crosses and stays in the slower, denser plasma beyond. This breathing motion of the boundary is caused by solar activity. When the Sun has strong outbursts, the increased solar wind pressure pushes the shock farther out. When activity drops, the shock moves inward. The boundary is dynamic, not static. Voyager 2 crosses the termination shock on August 30th, 2007, at 84 AU, 7.8 billion miles. Wait, Voyager 2 crossed closer to the Sun than Voyager 1 did, about 10 AU closer, 930 million miles closer. If the boundary is spherical, both spacecraft should cross at roughly the same distance. This is the first solid evidence that the shape is wrong. The heliosphere isn't a simple bubble. It's compressed in some directions, extended in others. Voyager 1 is heading toward the nose, the direction the Sun moves through the galaxy. Voyager 2 is heading more toward the side. The nose is compressed by the Sun's motion, like a bow wave in front of a moving boat. The sides and tail are stretched out. The two Voyagers are sampling different parts of a complex asymmetric structure. Scientists had suspected this might be the case. Now they have proof. After crossing the termination shock, both Voyagers enter a region called the heliosheath. This is supposed to be straightforward. Slowed solar wind plasma flowing outward and sideways. Turbulent, but predictable. A transition zone between the shocked solar wind and interstellar space. Scientists expect Voyager to spend 5 to 10 years crossing this region before reaching the heliopause. The heliosheath should be 10 to 20 AU thick. Based on Voyager 1's position and speed, crossing should happen around 2015, at about 100 to 110 AU. But starting in 2010, something unexpected happens. Voyager 1 begins detecting increasing levels of galactic cosmic rays. These are high-energy particles from supernova explosions and other violent events across the galaxy. Their intensity should increase sharply at the heliopause, not in the middle of the heliosheath. At the same time, lower energy particles from the Sun are decreasing. Solar particles should disappear at the heliopause, not gradually fade away beforehand. Voyager is still clearly in the heliosheath. Instruments still detect solar wind plasma. The magnetic field still has characteristics of the Sun's field. So, what's happening? In June 2012, Voyager 1 detects something completely new, a region where the magnetic field lines align directly radially, pointing straight outward from the Sun, not tangled, not twisted, perfectly organized. And particles are flowing along these field lines in both directions. Solar particles flowing outward, galactic cosmic rays flowing inward. The field lines are acting like a highway, connecting the heliosheath to interstellar space. Scientists call it the magnetic highway. No model predicted this. No one anticipated a structure like this could exist. The leading theory is that the Sun's magnetic field is connecting to the galactic magnetic field. Where field lines merge, particles can flow freely both ways. It's like a bridge between two otherwise separate regions. Voyager 1 spends about 2 months in this magnetic highway. During this time, cosmic ray intensity is higher than anywhere else in the heliosheath. Solar particle intensity is lower. The spacecraft is sampling a region with direct access to interstellar space, even though it hasn't crossed the heliopause yet. Then, on August 25th, 2012, everything changes. Solar wind particles essentially vanish. Cosmic rays jump to a high, steady level. The change happens over a few days, but the magnetic field direction doesn't change. It keeps pointing the same way it was pointing throughout the heliosheath. This causes confusion. Some scientists argue Voyager has crossed the heliopause. The disappearance of solar particles and surge in cosmic rays suggests it has. Others argue the lack of magnetic field rotation means it hasn't. Maybe it's in some intermediate region. Maybe the heliopause has multiple layers. The debate continues for over a year. Finally, in September 2013, NASA officially announces Voyager 1 crossed the heliopause on August 25, 2012. The spacecraft is at 121 AU, 11.2 billion miles from the Sun, far beyond where models predicted, not 90 to 100 AU, 121 AU, 20 to 30% farther than expected, 2.4 billion miles beyond the predicted boundary. This is shocking discovery number 1. The heliopause isn't where scientists thought it would be. And it's not just a small error, it's billions of miles off. This means either the solar wind is stronger than models assumed, or the interstellar medium is weaker than estimated, or both. Later analysis suggests the local interstellar medium is less dense than scientists thought. Not dramatically less dense, but enough to shift the balance point outward by 20 to 30%. This matters because the heliosphere shields the inner solar system from galactic cosmic rays. A larger heliosphere means better shielding. It affects cosmic ray exposure on Earth over geological timescales, which could influence climate, atmospheric chemistry, even mutation rates. But distance isn't the only surprise. Scientists expected the heliosphere to be roughly spherical, maybe elongated opposite the sun's motion, forming a tail like a comet, but basically symmetric. The reality is very different. The heliosphere is shaped more like a bullet or teardrop. The front, where the sun moves through the interstellar medium, is compressed into a blunt nose. The sides are flattened. The tail stretches out behind for potentially hundreds of AU. Voyager 1 crossed at 121 AU, heading roughly toward the nose. Voyager 2 crossed on November 5th, 2018, at 119 AU. Voyager 2 was heading in a different direction, more toward the flank. Both crossed at roughly the same distance from the sun. This tells us the heliosphere isn't dramatically elongated at the equator. The asymmetry is more subtle. The compression comes from the sun's motion through the galaxy. The sun moves at about 137 miles per second relative to the local interstellar medium. That's about 490,000 miles per hour. From the sun's reference frame, the interstellar medium is a headwind hitting the heliosphere from the front. This compresses the nose. Outside the heliopause, there should be a bow shock in the interstellar medium, similar to a bow wave in front of a boat. Models predict this shock at around 140 to 230 AU. But given how wrong the models were about the heliopause, the bow shock could be anywhere. The Voyagers haven't reached it yet. The shape matters for cosmic ray access to the inner solar system. If the heliosphere was spherical, cosmic rays would have equal access from all directions. With a bullet shape, they can penetrate more easily from some directions than others. The tail might provide an easier path for cosmic rays to reach us from behind. The shape also affects how the solar system interacts with structures in the interstellar medium. Our sun is moving through a region called the local interstellar cloud, a slightly denser patch of the interstellar medium, a few light years across. The boundaries of this cloud affect how the heliosphere is compressed. In thousands of years, the sun will move out of this cloud into a different region. The interstellar pressure will change. The heliosphere will change shape and size. The Voyagers are giving us a snapshot of the boundary as it exists now. Future spacecraft might measure a very different structure. This is shocking discovery. Number 2. The shape is wrong. Asymmetric, dynamic, influenced by the sun's motion through the galaxy. Not the simple bubble scientists predicted. Scientists expected crossing from the heliosheath into interstellar space to be relatively clean. A boundary where, over a few weeks or months, solar plasma disappears, cosmic rays increase, and the magnetic field reorients. A clear transition. Instead, Voyager 1's approach to the heliopause takes over 2 years. Starting in 2010, cosmic rays gradually increase, but the spacecraft is still detecting solar plasma. In 2012, it enters the magnetic highway, an unexpected structure where particles flow along field lines connecting the heliosheath to interstellar space. On August 25, 2012, solar particles vanish. Cosmic rays jump up, but the magnetic field doesn't rotate. This creates months of debate. Finally, scientists realize the galactic magnetic field happens to run roughly parallel to the Sun's field in this region. Pure coincidence. Crossing the boundary doesn't cause a dramatic field rotation because both sides point the same way. Voyager 2's crossing is different. It happens over about 1 day on November 5th, 2018, much faster than Voyager 1. And Voyager 2 detects a clear change in magnetic field direction. About 20 degrees rotation. Not a dramatic flip, but measurable. Why the difference? The two spacecraft crossed in different locations. The boundary structure isn't uniform. At Voyager, one's location near the nose, the heliosphere, is compressed. The boundary might be thicker or more structured. The magnetic highway phenomenon might be more common there. At Voyager 2's location toward the side, the boundary is sharper, the transition faster, the magnetic geometry different. Both spacecraft also detect oscillations after crossing. Voyager 1 briefly detects solar particles again in August 2013, nearly a year after crossing. Then they disappear again. The boundary washed over the spacecraft, then receded. These oscillations are caused by solar activity. Strong solar wind bursts travel outward through the heliosphere. When they hit the heliopause, they temporarily push it outward. The boundary expands past a spacecraft, then contracts when the pulse dissipates. Voyager caught the heliopause breathing, expanding and contracting in response to solar storms billions of miles away. The pressure wave from a storm in 2012 might not reach the boundary until 2014 or 15. This dynamic behavior wasn't predicted. Models treated the heliopause as stable, moving slowly over years in response to the solar cycle, not oscillating rapidly over weeks or months. Not moving enough for a stationary spacecraft to cross back and forth without actually moving. The boundary of the solar system isn't fixed. It's not a line you can draw and say, here it ends. The boundary moves, sometimes by several AU over short timescales. If you're at 120 AU, are you in the solar system or interstellar space? The answer depends on when you ask. Right now, maybe interstellar space. Next month, after a solar pulse arrives, maybe back in the heliosheath. A few months later, interstellar space again. This is shocking discovery number 3. The transition is complex, prolonged, and dynamic. Multiple crossings, the magnetic highway, oscillations, nothing like the clean boundary scientists predicted. Voyager 1 is the first spacecraft to directly sample the interstellar medium. Before Voyager, all knowledge of interstellar space came from remote observations, spectroscopy of distant stars, radio observations of hydrogen clouds, theoretical models. Voyager measures it directly, sticks instruments into it, and takes readings. The density is about 0.08 particles per cubic centimeter. The best vacuum chambers on Earth achieve densities around 1 million particles per cubic centimeter. Interstellar space is a better vacuum than we can create in our best laboratories, but it's not empty. 0.08 particles per cubic centimeter means 80,000 particles per cubic meter. A cubic meter of air at sea level contains about 10 to the 25 particles. Interstellar space is about 10 trillion times less dense than air, but it's not nothing. The temperature is about 54,000 to 90,000 degrees Fahrenheit. Sounds hot. But temperature measures average kinetic energy of particles, not heat content. With so few particles, even high temperature doesn't mean high heat. An astronaut in interstellar space would freeze, not burn. Not enough particles to transfer heat. The pressure is about 0.0000000000003 pascals. Earth's atmospheric pressure at sea level is about 101,000 pascals. Interstellar pressure is roughly 1/10 trillionth of Earth's. But this pressure balances the solar wind at the heliopause. Even though it's extraordinarily tenuous, it's enough to stop the sun's outflow. Voyager detects plasma oscillations in the interstellar medium, waves of compression and rarefaction traveling through the plasma. In 2012 and 2013, Voyager 1 detects several bursts of oscillations. The frequency allows scientists to calculate electron density. Different measurements give slightly different values. The density isn't perfectly uniform. It varies by 10 to 20% over distances of a few AU. These variations affect how the heliopause is structured. Denser regions push harder on the heliosphere from that direction. Less dense regions allow it to expand farther. The interstellar medium is also magnetized. It contains a magnetic field, part of the galaxy's overall structure. Voyager 2 measures the field strength at about 50 nanotesla. Earth's magnetic field at the surface is about 50,000 nanotesla. The interstellar field is about 1/1,000,000th as strong as Earth's. But over vast distances, even this weak field has significant effects. It shapes plasma flow. It accelerates cosmic rays. It connects star systems across the galaxy into a web of field lines. None of these properties match predictions exactly. Models suggested similar values, but actual measurements consistently differ. Density, a bit higher or lower than expected. Temperature, slightly different. Magnetic field strength and orientation, not quite what models predicted. Every measurement refines understanding and forces scientists to update models. This is shocking discovery. Number 4. Interstellar space properties don't match the models. The first direct measurements reveal differences in density, temperature, pressure, and magnetic field. Small differences, but enough to matter. One of Voyager 1's most surprising findings is detecting what scientists call tsunami waves. Shock waves traveling through the interstellar medium, caused by the sun. When the sun produces a powerful outburst, a coronal mass ejection, or strong solar wind burst, that pulse travels outward through the heliosphere. When it reaches the heliopause, it hits like a hammer. The impact launches a shock wave into the interstellar medium. These waves travel at the sound speed in the interstellar plasma, about 60 miles per second. Much slower than the solar wind, but fast enough to cross several AU in a year. Voyager 1 detects the first tsunami in October and November 2012. The plasma wave instrument detects oscillations lasting several weeks. Specific